Okay, good afternoon, everyone. Before we start, I would just want to make sure that all of you already registered to the course, right? I think only one student that just asking if you need food. Everyone, I think I don't need this. So I hope everyone already registered, right, at the very beginning. So if you need the code, or maybe if you have maybe your friends who want to join, I think we still have time until 19th, right? Adding courses, 19th, right? Until 19th, or this week at least, right? So if you have friends who want to join, they can come, or just email me to get the code. Okay, just send me an email, and getting the codes. Okay. And before we start, since we are still in the early chapters, and I will probably just give additional notes, and also some mathematical models to see how we can work out the differential equations. Okay. At least to show you how we can apply in really brief before we are going to the in your textbook, the next chapter, which is the chapter 2. We are going to move on to the first order differential equations, which start with the slope field and the autonomous order differential equations. Okay, and since we have not really expecting the schedule, we are a little bit behind what I've expected. So I think some short topics, maybe at the middle or maybe near the end of the semester, maybe I will skip some part of it. Okay, and I'm still not sure whether we are going to have the engineering mathematics 2. I believe we are going to have another engineering mathematics, so I will maybe shift some parts of the first one to the second. Okay, and we can focus more on the first order, second order, higher order, Laplace, the eigenvalues, and the vector calculus, and maybe not all vector calculus. And this the second part of the engineering mathematics, if it's happened, then we can start with the partial derivative, that is for the partial differential equations, and Fourier transformations, and so on and so forth, and another vector calculus. So I think we can focus our semester for that, and maybe some short topics we'll skip. Okay. Now let's get into our topics. So today, or maybe last week, we ends up with the existence and uniqueness. So this is happen when we have the differential equation and we know some initial conditions that is restricted to some points. Okay, and we are going to check whether that initial condition or initial value problem is really giving you some clue, at least, how the solution should be. Is it the solution exists or not? Okay? At that point, the AB, okay, this AB here, okay, and the existence means it's related to continuity. So I don't want you to really memorize all the words here, but the key points from this existence is continuity. Okay, is continuity. Okay, so you have A or you have B. The solution should be continuous around that point. Okay, that's the idea for these words. Okay, for all these words. Okay. So if the function itself is not continuous, then the solution is not guaranteed. It may or may be not. Okay. So it's not really guaranteed that it is a solution. So perhaps we are given some differential equations and then some initial condition, and we want to verify whether at that initial condition we are having our solution. Okay. Okay. Now the second one, after we know the solution exists, can we know whether the solution is really unique? Okay, it's exactly one unique solution. So the second part of it is the uniqueness. So the uniqueness will start with the dou f dou y. So or let me write if, okay, if is also continuous around the initial condition AB. Okay, if this is also continuous, which means the solution, then okay, the solution to differential equation at AB is unique, or maybe let me write with red color to make it stands out, is unique on the open interval around the initial condition, or maybe around, just take x equal a, which means it's actually a point, the point AB, okay? So we are going to check whether the this is actually not this, is Leibniz notation, sorry, to make it clear. So we are going to take partial on y, okay, for the functions from the differential equation. So let me just give you some practical insight on how we are going to use this exact and uniqueness, okay, at least to verify whether at some initial condition or at some initial value, we know that the solution will be exist or will be unique, okay. Because we know that in differential equations, if we are not restricting into some initial conditions, we are going to have family of solutions. That we are already given by the solution curve, that we have many curves that can be our solutions. Okay, so we need to have some restriction to know whether it's going to be the exact solution or the explicit solution. Okay. Maybe let me write, because I think you will be confused on this part here. Let me give notes here. Note that F is DE. Okay. Okay, let me flip the page and give you some example on how to check. Okay. Okay. Verify the existence and uniqueness. Let me start with the simple dE. Let's say we have dy over dx is equal to x squared y squared, and we have the initial conditions. Okay, this means the x is equal 1 and y is equal -1, or we can say that the point will be 1, -1. Okay. Now, of course, we can start with some assumption that let the fxy will be 2x squared y squared. And we know that from differential equation, if we look this 2x squared y squared, it's just a normal equations that is continuous everywhere, right? We can say that it's continuous everywhere. Nothing wrong with this. There are no any other specific domain that restrict the interval, right? So the interval of existence will be continuous everywhere. So we can say this will be continuous everywhere. So for this part, you just given by the equations and just to check the initial point or initial value, whether it is exact or unique. And then when we check the partial with respect to y, we get that this will be 4 x squared and y. We just differentiate with respect to y. And also, this is similar equations that just x squared y, and I believe this is also continuous everywhere. Okay, this is also continuous everywhere. So because this is continuous everywhere from the function of the differential equation, and also the partial one is also continuous, then we can say that at the point there is one there exists one unique solution. Okay. So practically, you can maybe figure out, like, when something happened within the existence or the uniqueness, maybe some restriction on domain that makes the, let's say, the functions become discontinuous, then there will be some interval that can make whether it exists only for some interval or maybe unique for some interval. Okay, we call that the interval of existence and uniqueness. Okay. Let me give you another example. Okay. So this is first example. Second example. dy over dx is equal x ln y, and the conditions is 0.11. Okay. Okay, now because we have ln, probably this will have some restrictions, and we can at least write some interval to make it exist or unique. Okay, so first we can write, let the differential equation become a function of two variables x, y. Okay, from here we know that the ln cannot be negative, the inside of ln, so we need to have it's continuous. Or maybe let me write with blue color. It will be continuous when y is positive, right? So the interval of existence, so it exists if y is greater than 0. And then try to find the partial. And we got this is x over y. Of course, because it's rational, the denominator should not be 0, right? And we can also say it will be continuous when x is not equal 0. So from these two, existence and uniqueness, we can say that there will be, so maybe let me write down here. So at 1, 1. At 1, 1, if we also plug in the numbers, there's nothing wrong with the numbers, right? It's okay. It's okay. We can write there is one unique solution, because 1, 1, the point, it's perfectly in our rule that is y is not 0 and y is positive. So 1, 1 is positive, right? Positive and not 0. So it's okay. So we have one unique solution, or exists one unique solution, okay? But, for example, if the points maybe change to negative, the initial condition become negative, then it will not be matched. So at the negative part, well, for example, if it is going to be negative, like for example this one, it will be maybe a negative 1, 1. Or maybe some other number that makes the y is negative. If y is 0 or y is less than 0, then not guaranteed to be exist. So first you can think the differential equations first, finds the interval of existence, and then do partials with respect to y, and also make sure that you get the interval of uniqueness. When you get the interval, you can check the initial value, whether it's also among the policy, okay, among the interval. If it's not, then it's not guaranteed or it's not unique. Okay? Well, it depends on the situation. Let me give you another example. Okay? Okay, and then perhaps another example. dy over dx equals square root x minus y, and the initial value is 0.22. Okay, the a is 2, b is 2. Or perhaps if you are maybe confused on the initial value, you can just see the differential equation first, make sure you know the interval of existence, uniqueness, and then you can check the numbers, check the value. If it is matched or supposed to be following the interval, then it should be okay. If not, then it's not guaranteed to be exist. Okay? So again, we can start with writing the functions of two variables x, y. So we can say from this x minus y, we can restrict the domain. So restrict the domain, this will be continuous for x minus y. We want to make it a real numbers. And we can say that this should be positive. Okay. But what's happened when it's 0? The square root can be 0, right? But what's happened when it's 0? So when it's 0, for example, if this is, let me write here, x minus y, if this happened, okay, imagine there is a curve, and if this is 0, which means that, let me write here, means that it is on the endpoint, and we don't want to be that way. Okay? It's on the either the left side or the right side of the curve, and we don't want to make that happen. Okay? We need to make sure that it's not on the endpoint. Okay? Because at the endpoint, of course, we cannot say it's continuous or discontinuous because it's on the endpoint. Okay? If we are on the between the interval, we make sure that they have continuity. Okay? So x should be greater than y. This is for the existence, so x should be greater than y. Now, if we take the partial, so we do some differentiations, and we are going to have 1 over 2 squared x minus y. And because we differentiate with y, it has negative, we need to multiply with negative. Okay. Okay, I hope some simple differentiation like this, not a problem. Okay. Let me just write some idea how would this happen. This is from here, and this is going to be here. Right? And this become negative, so we can write, or let me write, it's to multiply with dy of x minus y. And then it becomes this. Okay. Therefore, if you want to know the process. I think it's also resolving the same. X minus y should be positive. So we can say that because of our initial condition, so at point 2, 2, if we plug in, there will be inconsistency, right? So we can say that at this point, we cannot guarantee guarantee existence. Okay, I think just writing we cannot guarantee existence is enough. Okay? So first, finding the interval, checking the domain, and then after that, check the initial value. If the initial value is inconsistent with the interval, then we can simply say that it's not guaranteed to be exist. Okay, that is the existence and uniqueness. Okay, existence and uniqueness. Okay, now I will move on to some general mathematical models, okay, that might be in our discussion, but I will not go into details, just to show you some brief models. Okay? And I believe some of the models you already, I think, studied, at least on physics or maybe chemistry. Okay, let me move to the next page. Okay, so this part for existence and uniqueness, I'm just showing you how to verify. Okay, how to verify. So let me write some mathematical models. The models is like some formulations that is going to connect some phenomenon, okay, with some data, and then from there we can predict what will happen if we have some consistency, and we say we have some, probably we start with assumptions, hypothesis, and then the phenomenon itself, and then whether the models is aligned with the results or not. Okay? But I think I will just start with the something that is already studied before. The populations is very, very basic models. Okay? Populations. It's going to be the rate of population itself is proportional with some constant, okay? Some constant, and the number of the populations. Okay? So the number of population will increase according to some constant of, we can say it's proportionality constant. Okay? Will it happen with the populations as the humans growth, or maybe bacteria that is easy to control? Because if we looking at the human, we need to have like several factors, right? Several factors that will determine the K. So the K itself, it's not like really an exact number. It can be from other factors as well. Okay, like for example, the growth rate can be influenced by maybe the environment, what's happened during some period of time, and etc. Okay. Another way, the models that is widely studied is the decay, the radioactive decay. So it's similar to the populations, but now we have some decreasing numbers. Okay. So dA, it's related to, if this is P is population, the A is related to the nuclei. Nuclei of substance, okay, in which should be the substance itself will be decreasing according to some rate of the decay. And then law of cooling, I think mostly studied in physics for the decay and the cooling. This is the temperature that is decreased, the rate. It's proportional to some constant, so everything has the k here, the constant k. So this is T minus Tm. So the T is representing the temperature. So T is the temperature. Let's say of body at T time. Okay. And then the Tm is the T of the medium, or we can say the environment. So we can say it's cooling, but it actually works for warming. Okay, it's the same thing. It depends on the rate, whether it's going to increase the temperature or decreasing the temperature. And maybe some additional one here is probably for disease, like the spreading disease, like a virus, like current situations. We can also predict with some models. The simplest one, we just say that at some x, rate of x, we can say we have kx y. Why we need to have x on also y? Because the spreading needs to have the subject and object. Okay, so x, y is representing that models. Okay, so one person infected, and then it was spread to another person. Okay, and then this is perhaps getting more interesting, because if we don't know how fast the disease grows, then we are not sure how the virus will be spreading, which on how like the radius of the virus. Okay, so we can also predict that. Okay, so this xy representing, or we can relate this xy can be related by x plus y is equal n plus 1. So n is the fixed populations. So if one infected spread disease, then the x and y will represent this. Okay, and then we can write in another way, according to this n for the population itself. We can write kx and then exchange y with n plus 1 minus x. And perhaps we can assume that the initial value problem is at t0. We assume that the virus starts to spread when there is, we can say, 1% infected. So 1% infected at the beginning. So we can start at t0, the virus start to spread out. Okay, this is just to show you how we can make out the differential equations. Okay, not really a method or techniques in our engineering of math, but this is just to show you some simulations. I think the last part maybe related to chemical. So dx dt is equal, or let me write its chemical reactions. So dx dt is equal to k alpha minus, it's not x but x like that, just to show you that this is the amount of some moles or molars or the molecules that is forming. So x let me write X is amount of some molecules formed by chemical reaction. And alpha and beta will be amount of the first two chemicals A and B. So at the beginning you have A, B, and it will be reacted with some certain moles, and there will be some reductions, amount reduction from A, B, and that will be the X, okay, amount reductions. We can say that X is mostly in moles, okay, the standard that is easy to follow in chemical reactions. In case I will there will be something in exam, I will give you the equation and then you can just think through on how to deal with it. Okay? Yeah, I think this is models. There are other models as well, but I think I will just focus on this 5, right? 5 models. There are also models for the structure, the cables, the circuit for electrical. But I think let me just focus with this. If we have encountered other models, I will give you the equations and assumptions, and then you can just think through about it. Because the most important thing in our lecture is to know the basics, okay? To know the basics in engineering of math, some techniques, some methods, okay? Okay. Let me move to the next chapter, which is the first order, and we start with the slope field, okay? The slope field. Okay. So we move to the next section. It's the first order. Let me just write ODE, okay? First ODE. So to begin with, I will need to write that this there is solution curves without necessarily a solution. So what does that mean? So let me just write the introductory, some DE. Do not possess or have any solutions. For example, if we can write the dy over dx, or maybe just y prime, I think it's easy to write. Y prime squared plus 1 is equal 0. We can write that no real function satisfy this DE. Okay. Okay, that's the first one. The second one, some DE possess solutions that can be found analytically. We can say analytically with perhaps the implicit or explicit form. And perhaps to make this happen, we need to have some techniques, right? We need to have some techniques from integrations, perhaps need to have the tools, integrations, and other procedures, okay? And other procedures. So before we identify the solutions, what we are going to get through, the first step in the first order is to analyzing the solution of DE qualitative, okay, or qualitatively. Which means we need to have some tools to know or to simply observe what kind of solution it might be. So we need to have some tools. Okay, we need to have some tools. Okay. So to analyze, we need some tools. One way to see this qualitative, in our case in first order, is through the direction of the slope field, okay, or the slope. Okay. The tools is slope field. So what is slope fields? Okay, slope, I hope you still remember, slope is we can simply say it's the gradient, okay, the gradient. But fields means it's like, if you remember magnetic fields, like for example, let me draw like a magnet here. This is a kind of the fields, right? In one way, or maybe there are two. If you remember the magnetic. So what these fields mean in the slope fields, we are going to at least draw all possibility of the gradient, okay, of the differential equation. Because when we talk differential equations in the first order, that means we are going to talk about the curve of the gradient. Okay? So we can start with this dy over dx represent tangent line at specific points. Okay. So slope fields we can say that is our approximations based on a graph of slopes. Okay? So basically, let me just write small notes here. What we are going to do, the process, is we are going to graph a lot of, we say, little lines, or in your textbook, it's called the lineal element, but let me just write little lines to make it easy to be understood. That representing the slopes at certain points on x, y axis. And then after we graph all the possibility of the slope, and then we are given the initial conditions. Like previous sections, we always talk about initial conditions. And after we given by this initial condition, we can predict how the curve will be. Okay? Then we can approximate the fitting curve. Let me write here the fitting curve. Okay, let me just show you how. Okay, in the next page, more practical. And since this is qualitative and approximate, then the solution is not really an exact, like what kind of curve, but we can visually see from the slope, okay, from the slope. And also I will show you maybe some links on the GeoGebra that many people already make their own slope fields, and you can just put your equations and see the slope fields. Okay? But let me just show you how, okay, to practically use this method. Okay, so first we need to know what kind of DE. Okay, let me just show you this. Okay. So let's say it's x plus y. Let's start with the easiest one here. So first, we need to make the table for x and y. Okay. Let's say this is x, this is y. I think we can have break first. Okay. After that, we can go back to 10. If you want to write, if you want to write the notes, okay, and we can have some break.
permit.
Udah pekerjaan udah tuh.
Udah dapat. Udah dari Samar aku kemarin.
Mana sini? Di ini ya?
Iya, di situ.
Ini ya. Di mana nih?
Itu di Candu, Prof.
Oh, di Candu.
Iya.
Jadi ininya
Yang dalam.
yang dalam.
Yang masak-masak biasa.
Hari apa?
Aku Selasa, Rabu, Sabtu, Minggu.
Minggu. Ada berapa orang sih?
Dalam dapur.
Part time-nya?
Ada 4 di dapur. Depan 1. Terus sering ke Candu.
Pernah makan aja sih, tapi belum kesana. Mesen aja. Ada orang.
Yang NTST itu ya?
Tapi kayaknya dulu udah lama kayaknya saya mesen.
Cobain ya, ntar saya bakarin.
Oke.
Thank you, Bro.
Yuk.
Itu kenapa sih bermasalah terus Fight Club? If I want 4 minutes, I will just go back to Thailand. That will probably use it.
Okay, continue a little bit on the slope fields. My plan is actually after slope fields, a little bit of we call it autonomous order, and then that's it. And then I'm planning to have, as usual, an evaluation at the end. Last week I forgot, so this week I will send to you also for your attendance. Okay. Okay, let's see from this table. We just make a table to make out the x, y points. Let's say we can make the x and y from -4 to 4. Okay, well, I should have the square background, but I forgot them. Let me just write all this. Okay, let me just put the numbers from x plus y. So this is -8. This means that this is the slope at specific points. Okay. So -8, -7, -6, -5, -4, -3, -2, -1, and then this will be 0. Okay. If we continue around here, this will be 1, 2, 3, 4, 5, 6, 7, 8, and we can see some patterns here. So I think we can just set up all the numbers. Okay. Now from these numbers, we can set up another axis. So let's prepare our axis. Sorry. Okay. Okay, this is y-axis, x-axis. And we can start by maybe take into 4 units each axis. Okay, and then because we draw it manually, so we need to have some sense to differentiate the numbers for the slope. Okay, so it depends on how steep it is. Okay, it's actually it's up to you. Okay, but let's start with the 0, 1, which means the horizontal slope. 0 is horizontal slope. I think we can start with the 0, 1, which is 4, -4, 3, -3. So we can say that we have, we can start with x is equal 4, okay? X equal 4, and y is -4. So we can start from maybe here. So let me erase this. So that is our point. So we can draw a horizontal line like that, and this means that the slope at 4, -4 is 0. And of course, it also depends on how you cut the axis. Okay, it can also be like half 1/4. So it's practically just approximation. It's not really a good way to represent, but at least in general, it can represent your dy over dx. Okay, approximately. Okay, so we can start with that, and then maybe another one is around here, and another one is around here, and around here, and then also in 0. And then also with the -x, we have this also. So this is why we call this analysis qualitative. Okay? Qualitative. It's not really quantitative, not really exactly our solutions, but we can just see what kind of graph it can make. Okay. And then, for example, from this one, let me just name this -4, -3. Now we can see the -3 and 4 for x. So x -3, 4 is -7. So we are going to have minus slope. So minus slope we can make x plus y minus 3. Oh, wait. Minus 3 and 4. Oh, it should be here. Minus 3 and 4 here. Oh, it's 1. Okay, it's 1. Sorry. It's positive. So at minus 3 here, minus 3 and 4, it should be going to be maybe like this. Okay. Because it's equal 1, so it should be having at least around 45 degrees angle, right? And then increasing, -2 becomes with the same 4 here. This became 2, 3, 4, 5, 6, 7, 8. Go to the horizontal one. So we need to make it a little more steep, and then okay, I think I need to make it more clear. But let's say this is going to be more steeper, still steeper like that. But it's not exactly like vertical, because it should be infinite for the vertical one. So you should have like some limitations on that. This is to show you that the gradient is increasing, okay? Increasing. And then same way when you have this will be the same as this one, right? We have the pattern. I hope it's because it's difficult to draw manually. And then this is also the same. And then do all the things for the one here. Let me just make it clear. And then this part should be going to be -4 and 3 to make sure -4 and 3 should be 7. -4, 3, -1. So it should be mirror from the slope one. Okay. This is mirror, and then a little bit going here. Okay, you can see the rest of it. Okay, you can see, and then what this slope field does is, if you want to predict, for example, the initial conditions is maybe -1. Let me just focus on here because I haven't drawn this part yet. Maybe -1, 2, maybe here. Okay, so maybe -1 and 2 is around here. This slope here, okay? What is the most possible curve that we can fit through our slope field? Well, it depends on our drawing, but we can just approximate what will be, okay? So maybe it will go through by maybe around here, and continuing maybe around here. Oh, maybe this is our curve, okay? Approximately, because we don't really sure, because we draw manually. We have some error in our drawings, and then when we define the points, we define this. The difference is just 1 unit. If we can make sure that the errors is as small as possible, maybe 0.00 something, the points may be perfect, maybe smooth, but because there is some error that we can make when we draw manually, then we just need to at least approximate what kind of solution from the slope fields. Let me just give you the directly the slope fields, okay? Let me just erase this solution first, okay? So this is x plus y, okay? X plus y, I'm already making in the GeoGebra. So this is what we have, okay? So, and the person who made this, they also introduce you to the length of the slope and the density. So if we want to make it maybe like really, really low, and I think it's not really good for approximation because density is not much. The slope is not much for us to draw the line. Okay, so maybe we increase the density. Maybe this, the more you have, the curve will be more smooth and easy to fit. Okay, so it's actually, you can try GeoGebra, just typing slope field. There are several activities that you can choose. You can plug in the differential equations, and you can maybe, depends on the curve you have, you can maybe changing the axis, like maybe making more larger or maybe smaller. You want to see smaller versions. And the length of this slope, you can also change. Like the slope is changing, right? It's getting smaller, bigger. Okay. And then they also give you some example on solution. For example, a solution that we can make like that. But of course, we are talking about possibility of solutions. So there will be many solutions, depends on the points that you are going to observe. Okay? So for example, we can change the point here. We can change the point maybe around here. But if this is the one that you're looking for, this point, this 1, 2, this is your solution curve. Okay? At least visually, we can approximate and we can predict what will happen in the slow fields. Okay? So slow field is kind of like somewhat easy for some simple differential equation that you can draw each point with some slope. Okay? So if you can draw and then you can think what kind of solution that we have, you can draw like that. But of course, the difficult part is we're not really sure what kind of functions that is. But the visuals we can predict, we can visualize. Okay? So that's the slow fields. Okay? The slow fields. And you can put 4 solutions here, but you can also change like what kind of these solutions will be. Okay. So that is the slow fields. Okay. Okay, let me go back to our slide here, and let me just introduce you just a picture that is in your textbook. This is the example for the differential equations. At the beginning of our course, we have this dy over dx equal 0.2xy. And they already give you the slope fields here. And when you see the slope fields, we can predict the curve as well. And this is some solutions. Okay. And from the approximations, and of course using some software, they predict that the solutions or the family solution is y. And I think we can also write, I think before we also write this, right? Because when you derive this, it will go back to our dy over dx because it has y, one function that when you introduce differentiations that establish the original function is exponent, right? When we derive, the e is always there, okay? The e is always there. And the rest of it is just a constant or the chain rule from the original functions, right? When you derive, okay? So the only possible way is e. So the exponent in differential equation become important, okay? Because if we can make sure that when we derive, the original function is still inside or still included in the equations, that means the e can be a solution for many, many differential equations. Okay? And another example, like for example here, this is a slope field for the sine y, and the blue is for some initial conditions, that is when x is 0, y is -3/2. So because it's trigonometric, probably easier to follow with some radian. Okay, just to show you that we might have this kind of solutions. Okay, so we can approximate visually or qualitatively from the graph. Okay, and we call this is using the slope fields. Okay. Okay, now I want you to look at this dE, dy over dx equal to sine y. If we look at from the left side and if we move to the right side, we see that it's the same thing, right? It's the same thing because when we look at the differential equation, it's just having this y. There's no x here. So the only change that can happen is only on the vertical axis, right? Now we call this, okay, these terms, when we have only y in the differential equation, we call autonomous differential equations. Okay, let me just write in the next page. It's free of independent variable. Okay. So we call that as autonomous first order differential equations. So what does it mean? It means that the dE is free of independent variable. So we can say that if we have this form, dy over dx equal a function of y, and this will be autonomous. So we can also say it's free of independent variable, or the independent variable is not explicitly appear. We can also say that. Okay, let's see if we have dy over dx is equal 1 plus y and 1 minus y. Or we can say 1 minus y squared, also fine, but let me just factor as 1 plus y and 1 minus y. Okay, now as we did in, I think, previous calculus, when we did just like simple equation with x, we know that we can make out the, we say the critical points. Okay, the critical points in dy over dx is the critical points when it is having a 0, right? When dy dx of so dy dx 0 means that this will be our critical points, right? But now our critical points condition is we are having the dependent is y. Okay, so we can also say that when we have y equal -1 and y is 1, they are also our critical points, okay? In our case here, this is also our critical points. That will be symbolized by, when we have the line, this will be something that's similar to asymptote, okay? Let me just show you what does it mean, okay? Let me go through the graph first, just to screenshot the. So let me erase all this, and then let me just take 1 plus y, 1 plus y, and then brackets, open brackets, 1 minus y, and brackets. Okay, this is our curve. And then let me just take a screenshot, and then let me move to our slide, okay, just to make sure that, okay, let me just take this, take this, take this. Okay. Maybe this also. Okay. So let me put this into our page here. So this is our slope fields. Okay. And as I mentioned before, in the horizontal, if we take steps from x, it will not going to change, right? Because there is not x. There's not the appearance of x is explicitly it doesn't appear, right? So when we move from left to right, it will be the same slope fields, right? But when we look at the y-axis, it will have some changes. Okay, so let's look at when we have this -1 and 1. Okay, this so-called critical points. Let's just draw these critical points in, for example, here for 1. Okay, and the other one is here. Okay, so what will happen here? What will happen here? We have some characteristics. See from this below, middle, and the top one. If we can just take some random fitting curve, okay, just random fitting curve. For example, we start from the middle, okay, between -1 and 1. Okay, maybe we can start from here. Maybe it goes up here. Okay, maybe going there at the end. Maybe it's going to behave like so these two blue lines is acting like an asymptote. Okay, so it starts from here, from some -infinity, large -infinity. It's going here and here. Okay, and if you move this to the left to the right, it has some similar behavior. It has like this, right? Okay, if you move your hands, move the curve. Okay, and then look also if we have in the bottom. Let's say we have this, or maybe to make it more clear, maybe here. Or if you would like, we can translate this, shift the curve left to the right, and it has the same behavior. When it goes to the left here, it will reach, maybe with limit, going nearby this y equal 1, right? And the same thing when we have on the top. We are going to have the same behavior. And it's never going to reach this blue line. It's like an asymptote. So from here, let me write that that y equal 1 and y equal -1, it's acting as an asymptote. Okay. Okay, and when we see these three regions, if we compare the first one, the top one, and the bottom one, it somehow is getting crazy, right? It's getting crazy there, it's getting crazy here. But if we look at the middle, it's more stable. It's more stable. It doesn't go anywhere. Right? It doesn't go anywhere. We can say that this middle part here, we can say that it's asymptotically stable. And if we look the bottom one here, we can see that this is going to be unstable. Or we can say the stable one is when if solutions start near some points, let's say near A, then towards A as x goes to infinity. It means that it's going to reach the nearby the asymptote. Okay? We could say the unstable if solutions start near A, leave A as x going to be infinity. Or we can say also, if we have the other way around, when we look at the x goes to the other way around. Okay. Now this region, they gives also another method to predict. Okay, from the critical points. Okay, from the critical points. So from the critical points, let me write again the differential equations: 1 plus y and 1 minus y. Okay. Now we can predict not with the slope fields, but with just vertical line. And then it's simply similar to what we have done with the line number. When you deal with the inequality and make sure that it's positive, negative, the signs, it's similar. So let's start with the critical point. The critical point is 1 and negative 1 here, right? And what we are going to do is we are going to check the number in between or up here, down here, and then plug into here. Okay? And see whether it's negative or positive. So the method, when we check maybe with number 2, okay, positive 2. Let's start with 2. So 1 plus 2 and 1 minus 2. So it should be negative, right? Should be negative. So this will be negative. So let me write here a negative. This is a negative. And then between 1 and negative 1, maybe 0. Maybe it's positive, right? Positive. And then below negative 1, maybe negative 2. Negative 2, it's become negative. Positive, it's negative, right? It's negative. Okay. Now to deal with the this method, if you get negative, you make arrow downwards, facing downwards. If you get positive, you make arrow facing upwards. If you get negative, downwards. And we are going to see that it has this arrow, right? Okay. What does it mean? What does it mean? We can make sure, or we can confirm the stability of the solution. Okay? It's all stability of the graph. Okay? If this is facing like downward and upwards, it means it's attracted. So imagine something attracted. Intuitively, you can say it's stable or unstable. Stable or unstable. It's stable or not? If it's attracted. Stable, right? It's stable because it's somehow it's attracted. What doesn't mean it's attracted to the asymptote, which means it's more stable. So it gives stable equilibrium. Okay. And here it gives you unstable because it's going other way around, both sides, right? So it's more unstable. Okay. So I'm giving you like a simple way to see what is autonomous order and how we can analyze. Okay. I haven't yet given you the official what is this arrow means, but at least from this introduction for autonomous, I give you how we can visualize and then we can predict what kind of stability the asymptote will be. Okay. So I will stop until here. We can continue a little bit on Thursday, right? Thursday. And I want you to just go through my evaluations. Okay, my evaluations. Okay. So just use your smartphone, or if you use iPad, you can also use that as well. Just a simple questions from last week, just to make sure that we are on the same page. And I think not really having questions for now. Oh, sorry. Why it's closed? Okay. Oh, why it's happening? Okay, I think we can start. I think you can use your student ID for joining. If you forget, maybe later you can confirm with me. Let's just start. I think easy questions. Okay. I still remember. Because anyway, if you get wrong, then that's okay. That's okay. Okay. Remember that the focus is the y, or the dependent variable, not the independent one. Okay? You need to figure out which one is dependent and independent one. Who's Skids? Oh, okay. Okay, question 2. Okay, just a 30 seconds question. Okay. Okay. Last one. I give you a little bit, 1 minute around. So practically you can check one by one. But I think too short, right? The time? At least 2 or 3 minutes. Yeah. I think should be longer. Sorry. Well, more than one answer means it's two answers at least. Two answers. Huh? Yeah. Well, it's in between A, C, or E. Okay, it's supposed to be obvious. C. Yeah, sorry for the short time. It's strictly. Okay. Who is Ribbit? Ribbit and Johanna? Johanna? Who is Johanna? Oh, okay. Oh, yeah. Wait. Last one. Okay, last one. Please write your student ID. If you have any suggestions, you can also write it as well. You can write multiple times, so you can submit multiple times. Okay. Yeah, I think you already have it in the page, right? Or no? I don't know why this using iPad is like why it's always coming up. So yeah. Yeah.